Segment 12, the nature of light. Let's start with a few questions. What's a wave? A wave is a periodic disturbance that propagates. We have many different types of waves that we look at: water waves, sound waves, and light waves. Let's start with sound waves. How do sound waves work? A sound wave is what we call a compression wave. The local density of air is temporarily increased. That squeezes the air next to it, which then squeezes the air beyond it. And after this pressure wave goes by, the air will rarefy again. It will get less squeezed. So when I'm talking to you in a room, my vocal cords are wiggling back and forth. They're squeezing the air next to them, which squeezes the air next to them, which squeezes the air next to that, until eventually this pressure wave gets to your eardrum, squeezes your eardrum a little bit, pushing it back and forth, and your nerve cells behind your eardrum sense this motion and translate into sound waves. What I'm not doing is breathing in your ears. The molecules near my vocal cords stay where they are, and the molecules near your eardrum stay where they are, but the pressure wave is transmitted from one set of molecules to another across the space between us. In a pond, when you drop a rock in, you'll see a series of ripples moving out from where the rock landed. These surface waves in the pond you can characterize by two quantities: the wavelength, which is the distance between adjacent peaks, and the frequency, which is the number of times that a cork that you placed in one place would bounce up and down. What's light? Well, with light, we actually need two ways to think about it. First, as an electromagnetic wave, and also as a shower of particles we call photons. It's best to think of a photon as a wave packet, a bunch of light waves that move together in a group. The mathematical connection between these two pictures of light is given by the relation that the energy of a photon is equal to a constant we call Planck's constant, h, times the speed of light divided by the wavelength, or h times the frequency. The frequency of light is equal to the speed of light divided by the wavelength, because the number of times that something will wiggle up and down is equal to the speed of light divided by the spacing between the peaks. White light is a mixture of photons of different energies, or waves of different wavelengths. Let's go now and at least do a little bit of a demo about waves. You can look at the URL that's given on this slide by pausing for a second, and then go on the web and play with this little applet yourself. Here we have on the left a wrench and a string of beads on a string, and we're going to wiggle the wrench up and down and watch what happens. So now we have the one side of the string being wiggled up and down, and a wave propagates along the string. With this knob up here, we can change the amount of wiggling to change the amplitude of the waves or make it smaller. We can change the frequency with which the oscillations are induced by having that little wheel turn faster or slower, and you'll notice that the wavelength of the waves changes as we change the frequency. Now the wavelength is very long. If I make the frequency high, the wavelength will be very short. I can also change the tension on the string, and that will change its behavior as well. I urge you to take some time to go to this site and play with this tool to just get some feeling for how the waves behave. Electromagnetic waves, that is light waves, consist of an oscillating electric field and a magnetic field that are perpendicular to each other. The wavelength is the distance between two peaks of the field strength. The waves move along a single direction then at the speed of light, c. I said before that we can consider light waves as both waves and particles, and there are good arguments for either, and in fact we generally think of them as both. The wave nature of light is governed by the equation that relates the frequency and the wavelength we see here on the left. The electromagnetic spectrum is differentiated by wavelengths. We talk about the X-ray part of the spectrum and the visible part of the spectrum, as we'll be doing a little later. The primary evidence for the wave nature of light is diffraction and interference, which we'll talk about in just a minute. particles, we tend to speak of photons, and we use this equation E equals hc over lambda to describe the energy of each photon. In this case, the electromagnetic spectrum is differentiated by the energy of the particles rather than by the wavelength. The primary piece of evidence for this is something called the photoelectric effect, which we'll also talk about in just a minute. Let's first talk about interference. If I took out a pea shooter and I shot peas at a wall with a hole in it, if the wall was there, the peas wouldn't go any farther, and where the hole was, the peas would pile up in a pile behind it. So you would expect to see, as you sent light at a screen like this, a bright circle with a sharp edge where the light had penetrated the screen. What you in fact see is a fuzzy shadow, and this fuzzy shadow is caused by interference at the edges of the aperture. This is what we call diffraction. This is very important in astronomy because this diffraction effect happens at the edges of a telescope as well as at the edges of arbitrary holes. And it leads to slight fuzziness in the image, which limits our ability to separate objects that are close together or see fine detail. But the wave picture can explain a very commonly observed other effect called the photoelectric effect. And what that effect is if I take a piece of metal and I put it down and I shine light on it, if that light has a long wavelength or high or a low frequency, the photons have a low energy, and no matter how many photons or how much light, how bright the light gets that I shine on this plate, nothing happens. But as I bring the light to shorter wavelengths, to higher frequencies and higher photon energies, all of a sudden I cross a threshold where the metal plate starts to eject electrons. The electrons pop out of the plate and go flying off into the distance. And now, no matter how low I turn the intensity, no matter how faint I make the light, still a small number of electrons are popping off. This is called the photoelectric effect. This effect was first explained by Einstein in 1895, and in fact was the work that he received the Nobel Prize for. The photoelectric effect is the most easily seen manifestation of the particle nature of light. The interpretation is that photons, when they reach a certain energy, have sufficient energy to pull the electrons off of the plate when they're absorbed. But below that energy, they don't have sufficient energy, and no increase in the number of photons will cause the electrons to pop off of the plate. This brings us to Planck's law, which says that the energy of a photon is equal to this constant, Planck's constant, times the frequency of the photon. The higher the frequency, the shorter the wavelength, the higher the energy. This particle nature of light is important when we think about the way atoms behave. If you have a photon of just the right energy being absorbed by an atom in its ground state, the atom will jump to an excited state. And if the photon is not the right energy to make that transition, it will just pass straight through. Once the atom is in an excited state, it can relax again to the ground state and emit another photon, and that photon will have exactly the energy of the photon that was absorbed when the atom was excited, exactly an energy equal to the energy difference between the two different states of the atom. Only when the individual photons have exactly the right energy can they make this transition. A powerful light beam with photons of a different frequency would pass through undisturbed. So when you're the wrong energy, right through you go. But when you're the right energy, you get absorbed. So which is it then, a particle or a wave? Well, it really depends. It's both. And just as a general rule of thumb, we tend to think of photons or tend to think of light as particles when the energies of the individual photons are high, when we're at very short wavelengths, and when there are very few photons. And we tend to think of it as waves at long wavelengths where there are many, many more photons and where interference effects are much larger.